Have you ever really stopped to think about how your computer actually thinks? I don't mean in concepts or ideas, I mean its most basic, its most fundamental language. Well, today, we're going to pull back that curtain and decode it. Let's dive in. All right, so here's our game plan. We're going to start with the why, why there's this communication gap. Then we'll meet the 4 key players in this language game. After that, we'll get into the nitty-gritty of translation, I'll show you a clever shorthand that coders use, and we'll wrap it all up with a handy toolkit so you can do this yourself. Okay, so first up, the big why. You see, at its core, this is all just a communication problem. It's pretty simple, really. We just don't count the same way our computers do. And to get everything to work together, well, we have to be the ones to step in and play translator.
So let me ask you this, and think about it for a sec. The number 10, that feels pretty absolute, right? It's just 10. It means 1 more than 9. But what if I told you that in the secret language of computers, 10 actually means 2? Yeah, that's the crazy idea we're about to unpack.
So the difference really just boils down to this. We humans, we think in what's called base 10, or decimal. And it makes sense, right? We've got 10 fingers, so we use 10 digits, 0 all the way up to 9. But computers, they run on electricity. For them, a switch is either on or it's off. That's it. This creates a base 2 system, which you've probably heard of. It's called binary, and it only uses 2 digits, 0 and 1.
But here's the thing. It's not just a simple two-way conversation between us and the machines. To make everything work really efficiently, programmers actually use 4 key number systems.
All right, let's lay them out. You've got our familiar decimal, base 10. You've got the computer's native tongue, binary, base 2. But then there are these other 2, octal, which is base 8, and hexadecimal, which is base 16. Now check out the digits they use. Hexadecimal is kind of weird, right? Once it gets past 9, it just starts using letters, A, B, C, D, E, F, to represent the values 10 through 15. And believe it or not, you see this system all the time in stuff like color codes on websites or even in your Wi-Fi password.
Okay, now this is where the real magic happens. We're about to learn the most crucial skill in this whole thing, how to translate our numbers for the computer, and just as important, how to understand its numbers back.
Okay, so turning our numbers into binary. It's a surprisingly simple process. You can do it over and over. You just take a number, let's say the number 6. You divide it by 2. What do you get? You get 3 with a remainder of 0. So you write down that 0. Now you take the 3 and divide that by 2. You get 1 with a remainder of 1. Write that down. Last step, take the 1, divide it by 2. You get 0 with a remainder of 1. As soon as you hit 0 for the main member, you stop. Now here's the secret sauce. You read those remainders you wrote down, but from the bottom up. So that's 1, 1, 0. And that, my friend, is the binary for the number 6.
All right, so how do we go back the other way? Well, it's just as methodical. You just have to remember that every single position in a binary number represents a power of 2. You always start from the far right. That's the 1's place, or 2 to the power of 0. The next spot to the left is the 2's place, 2 to the power of 1, then the 4's place, and so on. You just multiply each binary digit, the 0 or 1, by its position's value, and then you add it all up.
Okay, let's make this real. We're going to take the binary number 1101 and translate it back into a number that actually makes sense to us.
So here's how we build the equation, piece by piece. Remember, each position has a specific value. Starting from the right, that first 1 is in the 1's place. That's 2 to the power of 0. The 0 next to it, that's in the 2's place, or 2 to the power of 1. The next one is in the 4's place, which is 2 squared. And that final one on the far left, that's in the 8's place, or 2 cubed.
And now you just do the math, and it simplifies really nicely. 2 cubed is 8. 2 squared is 4. The next spot is a 0, so that's easy, it's just 0. And anything to the power of 0 is 1. So that leaves us with this super simple sum.
You add them all up, and what do you get? 13. That's it. The binary number 1101 is just 13. We've officially translated from machine language back into human language. See? It's really that straightforward.
Okay, so you might be thinking, if binary is for computers and decimal is for us, why on earth do we need these other 2, octal and hexadecimal? It sounds like extra work, right? But they actually solve a massive problem, and not for the computer, but for the humans who have to program them.
I mean, just imagine trying to read a screen jammed-packed with thousands and thousands of 1s and 0s. It would be an absolute nightmare. Trying to find a single mistake in that mess? Forget it.
That's where octal and hexadecimal come in. They're just a compressed, much more human-friendly way to write out long strings of binary. A shorthand, really.
And this right here is the whole idea. Look at that on the left. You've got this long, intimidating, messy binary string. It's just a recipe for typos and headaches. Now look at the right. That's its hexadecimal equivalent. It means the exact same thing, but it's way shorter, it's cleaner, and it's just vastly easier for a person to look at and understand.
And you know what the best part is? The conversion is so simple. You don't need any complex math. To get from that long binary string to hexadecimal, you literally just break it into little groups of 4 digits starting from the right. Then you just convert each tiny group. And if you wanted to go to octal, you'd use groups of 3 instead. It's a really beautiful, elegant trick.
All right, we have covered a lot of ground, so let's kind of consolidate everything we've learned into a simple toolkit you can use to really master these conversions.
So let's lock in these key tips and tricks. First, that grouping trick we just talked about, that's your best friend. Use groups of 3 for octal, 4 for hex. It's a lifesaver. Second, if you ever need to convert between octal and hex, don't try to do it directly. It's a trap. Always use binary as the middle step, the bridge. Third, always double-check your work by just converting it back the other way. It's a super simple way to catch any little mistakes. And finally, just remember, like learning any language, practice is really the key here. It's what's going to build your confidence and accuracy.
You know, you should really take a second to appreciate what you've just done here. This isn't just about memorizing some random rules for numbers. No, you've actually gained a fundamental understanding of how our entire digital world is built. You've learned the basic grammar that's underneath every single app, every website, and every piece of software you use every day.
This knowledge, it's like a key. It unlocks a much deeper level of understanding. You've just taken a huge first step from being someone who just uses technology to being someone who actually gets how it works from the ground up. So I'll leave you with this question. Now that you can decode the secret language of computers, what will you build with it?